Hi guys. Today we're doing the 2.3 notes on biconditionals and definitions. Last time we talked in 2.1 and 2.2 about our conditional statements, and then we had the converse, inverse, and contrapositive, right? So if you see, we had this symbol summary, a conditional statement P implies Q, the converse Q implies P, right? You switch them. The inverse, you negate them both. Contrapositive, you switch and negate. So moving on to 2.3, biconditionals. So if a conditional statement and its converse are both true, we say the original conditional is reversible. Find my pen. Yep. Is reversible. Pretty sure I spelled that incorrectly. Reversible. Spelt. Nope, I did. Perfect. So we say the original one is reversible. Since both P implies Q and Q implies P are both true. If it is reversible, you can write it as a biconditional. A biconditional uses the words if and only if, right? And is now written with a double arrow, as you see there. So if my conditional statement is, if today is Saturday, then yesterday was Friday. Is that true or false? Well, that would be true. So if I do the converse, right, switching the hypothesis and conclusion, would say if yesterday was Friday, then today is Saturday. Is that true or false? That is still true. Since the conditionals is true and the converse is true, we say it is reversible and the biconditional will be true. So instead of having two different statements, if-then form, we have one biconditional. Today is Saturday, if and only if yesterday was Friday. A true biconditional statement implies that both the original or the conditional and the converse are true. Symbolically, today is Saturday. If and only if yesterday was Friday, we can write this with IFF. So if and only if. So if you ever see that if word spelled with two F's, that means if and only if, or you'll see it as a double arrow as shown above. So now we're going to test the statement to see if it is reversible. Remember, reversible means both the conditional and the converse are true. If it's reversible, we're going to write it as a biconditional. If not, write not reversible. So number 1 says, if a whole number is a multiple of 2, then the whole number is even. Is that true or false? That would be true. So I'm going to write it as now the converse would be, if the whole number is even, then it is a multiple of 2. Is that one true or false? Well, that one is true as well. Therefore, it is reversible, hooray, hurrah, and we can write it as a biconditional statement. A whole number is a multiple of 2. If and only if the whole number is even. Hooray! This is a biconditional statement because I used that phrase, if and only if, which is what you use for a biconditional statement. Number 2 says, rabbits are animals that eat carrots. When I go to write the converse, that would be if an animal, well, the original one, the conditional in if-then form would be if an animal is a rabbit, then it eats carrots, right? So actually, let me go ahead and write it as an if-then statement first. If an animal is a rabbit, then it eats carrots. And is that a true statement? That should be true. So then I do the converse. If an animal eats carrots, then it is a rabbit. And is this one true or false? Think about it for a moment. Now I need an animal that eats carrots. Are there other animals that eats carrots besides a rabbit? There are, in fact, so this is false. And since one direction is true and one direction is false, it is not reversible. Therefore, you cannot write this one as a biconditional. I'm running out of room, but you would say something like not reversible. Now, take a moment and see if you can read the biconditional statements in 3 and 4 and extract the 2 conditional statements. So take the biconditional given and write 2 different sentences in if-then form, one conditional and one converse. Moving on to the second page of this note packet for 2.3, it says, to apply logic and reasoning to the objects around us, we need to establish the facts. We already agreed there are 3 undefined terms. And what are those undefined terms? Well, they are point, line, and plane. And remember, these are accepted without proof. We also have several definitions. All definitions can be written in if-then form. A good definition is reversible. See if I can get some highlighting. It can be written as a true biconditional, and it's obviously clear and understandable, right? If you're going to define something, we need to know exactly what it's referring to and be able to quickly determine if something follows that definition or not. So, if we read 5 and 6, it says, state whether each statement is a good definition, explain your answer. Number 5 says, a square is a rectangle with 4 congruent sides. Well, can we first write that as a conditional statement? Sure we can. A square, if a shape is a square, then it is a rectangle with 4 congruent sides. So, we can write it as a conditional. And is that conditional reversible? Well, if a shape is a rectangle with 4 congruent sides, then it is a square. That one is also true. So it is reversible. It works both ways. It can be written as a true biconditional. If a shape is a square, a shape is a square if and only if it is a rectangle with 4 congruent sides. That works. It's clear and understandable. We're only using words, vocabulary words that we know for each one of those statements. So this is exactly a good definition of a square. So square, yep, it checks off all of our check marks. Number 6, a juice drink is a beverage that contains less than 100% juice. Well, first off, can we turn that into a conditional? If a drink is a juice drink, then it is a beverage that contains less than 100% juice. Okay, that's true. If we reverse it, if a beverage is a juice drink, then it contains, nope, that's the same direction. If we reverse it, it says, if a drink is a beverage that contains less than 100% juice, then it is a juice drink. Is that always true? No, right? So this one fails our reversible check, which means it also fails the conditional check, since there are lots of beverages that are less than 100% juice, water being an excellent example of one. Therefore, 6 is not a good definition. So, if we want to create a good definition for some of our mathematical geometry terms, we need to keep these rules in mind. It has to be reversible, so we can write it as a true biconditional, and it needs to be clear and understandable. Avoid using vague words like big or small. For instance, number 7, if two angles are complementary, so now complementary is our vocab word that we're defining. If two angles are complementary, then their sum of their measures is 90 degrees. That's a good definition. If we were to reverse it, if two angles sum to 90 degrees, then they are complementary. That is true as well. So that is an excellent definition of complementary. So take a moment and think about what good definitions would be for the words obtuse and right. Write them down, making sure that your definitions are reversible and clear and understandable so they can be written as a true biconditional statement. When you think you've got a good definition for both obtuse and right, go ahead and check the key on Google Classroom or on my website to see if you are good. And that does it for the 2.3 notes. Have a wonderful rest of your day.